Okay, so moving on. So let's dive into the first law of thermodynamics. All right. So the first law of thermodynamics says, don't talk about thermodynamics. No, I'm just kidding. That was a little Fight Club humor. Okay. The first law of thermodynamics says the internal energy of an isolated system is constant. Okay, well, that cute little song I played for you, right? Another thing you could say about the first law of thermodynamics, the internal energy is equal to the work plus the heat. Okay, it's as simple as that. Okay, and so you can see I've written it in two ways, and I want you to get used to seeing the first law in two different ways. Delta U equals W plus Q, or du equals dQ plus dW. Okay, so this is for measurable changes. And by measurable changes, I mean what we can actually accomplish in the lab, right? Because that's final minus initial. If I can measure simply put, if I can measure the temperature of something from its initial state to its final state, then I can measure what its accompanying change in energy must be. Okay, so what does this thing mean? Well, this is, assuming I can spell infinitesimally small changes. Okay? And so when we're talking about infinitesimally small changes, we're kind of saying use calculus. Okay? So this is the type of relationship we're going to be able to use to exploit other relationships. When we go down the rabbit hole of deriving equations and physical relationships and, right, connecting bulk properties to molecular properties, we want to use the expression of U for infinitesimally small changes. Okay? And so now we arrive at our first definition for work, and I'm going to give the very correct definition for infinitesimally small changes, not for measurable changes, but for infinitesimally small. Okay? dW, by definition, is negative F times dz, okay? A force acting over a distance, all right? So the unit of force is Newton. The unit of dz is meter. So a Newton meter is a kilogram. A Newton is a kilogram meter per second squared times another meter gives me a kilogram meter squared per second squared, which is a joule. Okay. And so there are several other, so this is the definition of work that I want you to kind of start thinking of. All right. There's a couple other definitions of work that I'll just use as examples. One of those is actually surface tension. And so you might be used to the definition of surface tension that says the resistance a liquid has to spread its area, okay? Well, another definition of that is the work required to bring a molecule across an interface, right? So if you think about like some interface, okay, and by interface, I mean like liquid on this side of the line and gas on this side of the line, if I try to bring a molecule across that interface or the other way from liquid to gas, there's work required. I have to apply work over some distance to make that happen, okay? And that's related to surface tension. And so I could write surface tension is dW, still work, infinitesimally small changes, but now this by definition is sigma times dA, okay? Where sigma is my actual surface tension, and that has units of Newton per meter, okay? And then, of course, dA would be my change in area. That's related to that definition, the resistance of a liquid to spread its area. And so we know that that is meters squared. So when you multiply that by meters squared, you get a Newton meter, and we recognize that a Newton meter is a joule. Okay. Another definition of work that we rarely think about, but electrical potential. That's work. Okay, the work required to move an electron through a potential barrier. Think about it. When you're doing chemistry, you're doing work. You're putting electrons into new orbitals, right? You're making new chemical bonds. That is a force acting over a distance, right? There's some force that's required to penetrate that electric potential from the orbital, and that electron has to move over a distance, okay? We could also just think of it simply as moving an electron through a wire, right? So think even bigger. So when I talked about that chemical reaction, right, that'd be molecular, but think about a bulk property. A bulk property would be just literally plugging in my cell phone charger, for example, and the electrons flowing through that wire. Well, they have to have a force acting over a distance to make that happen. So we could say the electrical potential, the work due to electrical potential, is often given as phi times dq, okay, where this phi is going to be my potential in volts, right? That's my potential voltage. And this dq is a change in charge, okay? Which is given as a coulomb, right? And so if you take a volt times a coulomb, you get a joule, all right? So we're mostly going to be playing with this definition here, okay, basing it off of the true, like, the simple root force over a distance. But I just wanted to draw these two examples. Surface tension and electrical potential are both examples of thermodynamic work, okay?